So, we defined something called as the flat band voltage. So, when at equilibrium the bands need not be flat, it will be flat only when phi m is equal to phi s, but that need not be the case, and this phi m minus phi s is the driving force for any band bending at equilibrium. But now when we start applying a gate voltage, we take the semiconductor, we take the MOS capacitor out of equilibrium, and when we make Vg equal to Vfb, we achieve flat band, all the bands become flat. So, that is like a starting point for all our experiments, all the bands are flat, okay, and we need to create this kind of an offset voltage to make all the bands flat. When we make Vg less than Vfb, we bring the majority carriers at the interface. So, in this case, so here we are all talking about only a p type semiconductor, okay. So, the same arguments hold for an n type semiconductor, the only thing is you need to watch for the electrons being the majority carriers and holes being the minority carriers, okay. But here we are talking about a p type semiconductor. So, when Vg is less than Vfb, we bring holes to the interface, okay. So, the holes start appearing at the interface, and this mode of operation is called as an accumulation mode of operation. So, it is again a technical term. So, when we say that the MOS capacitor is an accumulation mode operation, it means that the gate voltage is such that the majority carriers of the semiconductor are at the interface. And then now let us say we start making Vg greater than Vfb, but we are still less than Vt. Vt is our threshold voltage. So, Vg is sitting somewhere between Vfb and Vt. Now, what happens in this case is that the gate metal now has positive charge, okay, and therefore, it has to be balanced by the negative charge from the p type semiconductor, and that is done by depleting the semiconductor. So, this is the depletion, this region is all depleted. So, ideally speaking, there are no free carriers in that region. So, the insulator semiconductor interface is depleted, okay, and all the, in this case, all the negatively charged acceptor ions are exposed and they are balancing all the positive charge on the gate metal, and this mode of operation is called as the depletion mode of operation. Depletion mode of operation. And then when you start increasing Vg further and further, you will reach a point where the EI starts going below EF, EI starts going below EF at interface, okay, and electrons will start appearing at the interface. So, when EI has just started going below EF, it is something called as weak inversion, and when EI has gone well below EF, and when the electrons at the interface, when the electron concentration at the interface matches the hole concentration in the bulk, we say that the semiconductors, the MOS capacitor is strongly inverted, and this happens at Vg equal to Vt, and when you make Vg greater than Vt, all the excess positive charge in the gate is now mostly compensated by the electrons rushing at the interface and not so much by the depletion, charge. So, the depletion width stops increasing, okay. So, initially, so this is the story. So, initially you had flat band, when you start making Vg greater than flat band, the first thing that happens is the depletion width. So, let us say that is the interface, the depletion width starts increasing, okay, it uncovers more and more positive charge, but the moment the electrons start appearing at the interface, this increase in the depletion width more or less stops, because a small increase in the gate voltage will exponentially increase the number of electrons at the interface, and therefore, you have a lot of electrons coming in there to balance any positive charge, okay. So, that is the story of everything that is going on in a MOS capacitor. So, to go back and look at the band bending picture again, just to make things clearer. Okay. So, the moment you hit inversion, so you see this bending. So, initially it was just bent like that. So, that was the depletion operation, and the moment it started bending like this, you have an equal number of holes and electrons at the interface. Okay. And then when you start bending it further down, you have more electrons at the interface than the holes, and finally reach a point when the electron concentration at the interface matches the hole concentration in the bulk, and that is what the definition of our threshold voltage is. Now, if you still increase the gate voltage further, this band will not move too much more. Okay, it is not going to bend this much. Okay, because now the electrons have started appearing at the interface in large numbers. So, beyond this point, this band bending is not going to increase too much more. I mean, you need to really make your gate voltage very large for you to see any significant movement in the band bending. And that is because for any small movement, the electron population increases exponentially, and therefore, you have a lot of electrons coming in that easily balance all the charge on the gate. So, you really need to make a significant amount, you need to add a significant amount of positive charge on the gate in order for you to see any movement in the band bending. And therefore, after inversion or after threshold or after strong inversion, you could say that the band bending is, the bands are almost pinned. Okay. So, they are almost pinned at this point, they are not going to move too much. Okay. And another technical term which I should have probably mentioned is to define this potential. So, let us say I create this voltage, this built in potential as a reference. Okay. So, let us say that is the reference potential. This potential, which is the total amount of band bending in the semiconductor, has got a special term, and it is called as the surface potential. Phi s is the surface potential. Okay. So, that is the complete band bending in the semiconductor. So, at threshold voltage, what is the surface potential? The surface potential is going to be 2 phi f, because it is going to be phi f here and phi f there. Okay. So, when surface potential is equal to 2 phi f, your V g is equal to your threshold voltage. So, this is a very useful term to remember, because we will keep referencing this particular term. And since we have defined the surface potential, and if you define the voltage drop across the oxide, you can now, the summation of the voltage drop across the oxide plus the surface potential has to be equal to V g minus V f b. Okay. So, now how do we define threshold voltage? Okay. So, let us now start coming to a more quantitative definition of threshold voltage, because it is such a useful modeling parameter. But you must remember, as I mentioned, the semiconductors, the electrons are not waiting for the threshold voltage to, for the gate voltage to cross the threshold voltage before they invert. I mean, there is some weak inversion happening even before the surface potential reaches 2 phi f. Okay. So, the moment the surface potential increases beyond phi f, you have electrons appearing quite rapidly at the interface, and these are all the thermally generated electrons here. Okay. So, now let us say how to define threshold voltage. There are 3 milestones, right. You need to cross these 3 milestones. So, how do I define V g in a more quantitative manner? So, V t looks good, but what is V t exactly? What does it depend on? So, there are 3 milestones. Firstly, let us make the bands flat. Okay. We do not know what the equilibrium gives you. So, let us first make the bands flat. So, V g has to first cross. So, V g must first equal the flat band voltage. Okay. After that, we keep increasing V g, you start depleting the interface. The bands you have EF, initially that was EI, it is all flat band. Okay. So, that is let me just draw this clearly, that was EI, it is flat band, and now you start depleting the interface, the EI starts bending a little, okay, and you start having depletion, and then you keep bending a bit more, you still have depletion. So, you then have to cross the second hurdle, which is you not only have added a flat band voltage, but you start depleting the semiconductor, and this total depletion charge by Cox, okay, or the insulator capacitance is the effective voltage that you need to add. And then you still keep adding more and more positive charge, this is still not enough, you have still not reached threshold, you keep adding more and more positive charge, and now you will see EI go below EF, and now the electrons have started appearing, but we have still not reached threshold voltage. We reach threshold voltage only when the surface potential equals 2 phi f. Okay. So, the third milestone is to make EI bend, the EI minus EF at the interface have the same magnitude as the EI minus EF in the bulk, or in other words make the electron concentration at the interface match the hole concentration in the bulk. So, the hole concentration in the bulk and the electron concentration at the interface are the same. At this point the surface potential is 2 phi f, and you have added enough charge to make Vg equal to Vfb plus the depletion charge plus 2 phi f. And when you have added enough charge to make all this happen, then you can say that you have reached threshold voltage, and therefore, the threshold voltage has got these three components. It has got Vfb, which is the flat band voltage, it has got Q depletion by Cox, and I put a minus sign here because in this case it is all the acceptor ions, you will see, because the Q depletion has got a negative charge, it is negatively charged acceptor ions. So, you first reach Vfb, which is the flat band voltage, then you deplete the semiconductor, and finally you make the surface potential reach 2 phi f, and it is only when these three happen that you could say that there is enough charge in the gate that from this point on the semiconductor is strongly inverted, or the MOS capacitor is strongly inverted, and that voltage is the threshold voltage. So, in some sense this is the definition of the threshold voltage. Now, let us start getting into the details of these little terms here. So, what is Vfb, what is Q depletion, what is the Cox, what is phi f? Okay. So, what are these things? Cox is the gate insulator capacitance per unit area. Okay. So, it is the gate insulator capacitance per unit area. So, it is not the total capacitance. So, since it is per unit area, what does it depend on? So, let us say the insulator has got an permittivity of epsilon ox for the oxide, okay, and it has got a thickness of T ox. The total capacitance would be C is equal to epsilon ox A by T ox, where A is the total area. But since we are looking at the per unit area capacitance, C ox is simply epsilon ox by T ox. So, that is your C ox. Okay, so, we understand that term. What is Q depletion? So, this is something you are already familiar with, you have solved Poisson's equation enough number of times that you know that in a p type semiconductor which is depleted, you have QNA as the charge minus QNA, minus acceptor ions are all negatively charged, minus QNA is the charge per unit volume in the semiconductor into the depletion width, right. So, you have that is XD, and you have this minus QNA is the total charge per unit volume, and there is some area but since we are looking at charge per unit area we do not really worry about that. So, QNA into XD. Okay. If you had some area, QNA into A into XD would be the total charge present, because this charge per unit volume, sorry, there is a part of it which is not visible on the display here. So, minus QNA A into XD is the total charge present, because this is charge per unit volume, that is the area and that is the depletion width, but the charge per unit area is simply this term. So, that is your depletion charge. So, that is the amount of charge you need to put on the gate that is completely balanced by the depletion in the semiconductor. Okay. So, you understand what this is, you understand what this is. What is VFB? VFB is simply your phi ms, that is what is driving all this. So, it is the phi m minus phi f, phi s, okay, we call that as phi ms. So, you understand what VFB is. Now, VFB can have more complications, we will come to these things later on, but for now it is phi ms. And what are these complications? These complications are that you could have charges trapped in the oxide, you could have so that is one complication that we will look at. So, that will change the flat band voltage. But for now your VFB is simply phi ms, that is the driving force for all the band bending at equilibrium. And what is phi f? 2 phi f is the surface potential at the interface when you have hit threshold voltage. But what is phi f? Phi f is the EI minus EF by Q in the bulk, right. And how do you know what is EI minus EF by Q in the bulk? So, if you know the doping concentration, if you know Na, you can say Na is approximately your P, and P by Ni is equal to the exponential of phi f by kT, Q phi f by kT, and therefore, phi f is nothing but kT by Q into logarithm of your Na by Ni. So, that is your phi f, and we have already done these kind of calculations before. So, if you know the doping concentration, you know the intrinsic carrier concentration, you know what phi f is. Okay. So, this is the threshold voltage. Now, we are still not happy with this definition, right. So, what is XD? We have not defined XD, and how do you define XD? You solve Poisson's equation. So, we have done this many times. You just write, you assume full depletion, you make the assumption of full depletion, that is there are no free carriers, therefore, Poisson's equation is simply this term here, and therefore, your XD, your potential turns out to be this term. So, I will not go through these details, I think all of you are now at this point familiar with all this. That is the potential, and if you say that the bulk is at 0 potential, the interface, so the bulk is at 0 potential, the interface will have a potential of this term here, and that is the surface potential. So, that is the surface potential at the interface. And what is XD? XD can be written in terms of the surface potential as this. So, what is the surface potential again? It is, you have your, we are imagining the intrinsic Fermi level bending this way. So, if you keep your bulk as the reference, so let us say that is reference or ground, it is this difference. So, that is your surface potential. So, the surface potential equals 2 phi f, then we have reached threshold voltage. Okay. It could be less than 2 phi f, but when you reach 2 phi f, it is threshold voltage, and when surface potential is greater than 2 phi f, you are above threshold. Okay, but as I mentioned that after inversion the surface potential is more or less pinned, it is not going to, bands are not going to bend too much more. Okay, the surface potential is more or less pinned, and therefore, you can now say the threshold voltage is VFB, which is now written out as phi ms. This is Q depletion by Cox, because now we have taken into account XD. Okay, so, you multiply, so Q depletion now becomes Q, I have taken care of the negative signs, we have removed all that. So, Q Na into XD, okay, that is Q depletion is the charge, depletion charge per unit area, Q Na into XD, and for XD you substitute this term, here and you will end up with this being the value for Q depletion, and that is Cox. We already know what Cox is. It is the capacitance, the oxide capacitance, the insulated capacitance per unit area plus phi s, and at threshold phi s is 2 phi f. Okay. So, that is the threshold voltage. So, if you know the doping concentration, you basically know phi f, and so here again, here the surface potential term inside has been substituted, 2 phi s have been substituted for the surface potential term. So, that is why you have phi f there. If you know the doping concentration, you know phi f, you know this, you know if you know epsilon ox and T ox, you know C ox, that is the permittivity of the semiconductor, and that is the work function difference between the metal and the semiconductor. So, this work function difference divided by Q. So, this is the potential term, it is a potential, and you end up with the threshold voltage, which is a very useful modeling parameter. So, here are some very important or useful relations. We will sort of summarize all this by these equations here. So, VGS minus VFB. So, let us say, so let us do pardon this usage of S. Okay. So, that is just a force of habit. So, you can say S is the reference potential here. So, once we learn MOSFETs, you will understand what VGS is, but just replace all S with just VG. Okay. So, you have VG minus VFB is the driving force, that is the X. So, when VG is equal to VFB, you have flat band, there are no voltage drops anywhere, but when VG is different from VFB, you start having electric fields in the oxide and in the semiconductor, and therefore, you have some voltage drop across the oxide and the semiconductor. So, the first key relation is that VG minus VFB, that voltage has to be split between the oxide and the semiconductor, and in the semiconductor it will appear as the surface potential. So, let us say that is the drop across the oxide, the remainder of it will be seen as the built in or the surface potential in the semiconductor. So, Vox plus phi s is equal to your Vg minus Vfb. But what is Vox? Think of the semiconductor like this. Okay. So, you have the gate metal, you have the insulator, and you remember this is a MOS capacitor, right, and you have the semiconductor, and all the charge here is being compensated by all the negative charges in the semiconductor, be it depletion charge or be it electrons. So, this is your MOS capacitor in action, right. So, what is this? If you think of it as if you use your old, your conventional capacitor notations, that is Cox, okay, that is the oxide capacitance per unit area, into Vox is the voltage across this capacitor, right. That is the voltage across the insulator, that is the voltage difference, voltage drop across the insulator, that is Vox. So, Cox into Vox has to be the charge stored on the gate, okay, and the charge stored on the gate is the charge in the semiconductor, okay. And what is the charge in the semiconductor? It is a summation of the depletion charge and the inversion charge, okay. So, Cox is all per unit area here. So, therefore, your Cox into Vox is equal to the depletion charge plus the inversion charge, and I put a negative sign because all this is negative charge for this example, and therefore, your Vox is simply the depletion charge per unit area plus the inversion charge. By inversion charge you mean the electrons that have appeared at the interface, the inversion, the minority carriers. Okay. So, you have the depletion charge, you have the inversion charge divided by Cox is your Vox, and now we will substitute for this Vox here, and what do you get? You get Vg minus Vfb is Vox plus phi s, okay. But we have already defined the threshold voltage, is not it? So, the threshold voltage is Vfb, it has the Q depletion by Cox and it has got the phi s term in it. So, if you replace these three terms with the one term which is the threshold voltage, what we are essentially saying from all these equations is that Vg minus Vt, that is the excess gate voltage above the threshold voltage, okay, and that is something called as the overdrive voltage. It is helpful to know this term in case you hear this in the context of MOSFETs, what they are saying is it is Vg minus Vt. Okay, so again let us just replace all this as Vg. Okay. So, Vg minus Vt, because I have now gotten taken care of these 3 terms, is simply your Q inversion by Cox. So, what you are saying is that if you want to know how many electrons are there at the semiconductor insulator interface, you want to calculate, you essentially want to calculate Q inversion. What you need to do is simply say that Q inversion is equal to Cox into Vgs minus Vt, okay, the magnitude of Q inversion. So, Vgs minus Vt is the voltage, excess voltage above the threshold voltage, because till threshold voltage you did not have inversion charge or you do not have a lot of it, but above the threshold voltage you start having inversion, and therefore, the excess voltage, so everything that go, all the Vgs, what this is saying is that all the Vg above the threshold voltage is creating electrons at the interface. And you can further write Q inversion as Q into N, okay, where N is the number of electrons per unit area, and therefore, here you have the number of electrons. If you want to know how many electrons are there per unit area at the interface, that is the answer. Okay, so, that those are some useful relations which will help you imagine the situation a little better. So that you are not surprised when we just start writing these equations. So, it all comes from this basic understanding or this description of the device so far. The other relation, okay, now how do you find out what phi s is, okay, because you have one equation, okay, but I still cannot calculate phi. I know what Vg is because I am applying Vg. We can find out what VFP is by looking up the metal and semiconductor work functions, but we still do not know what phi s is, okay, because we do not know what Vox is. Okay, Vox is all this term, but we cannot calculate it without calculating phi s, because your Q depletion is also dependent on phi s. Okay, so you see it is a quadratic relation. Your Q depletion does depend on phi s, and you also have a phi s there. Okay. So, we need another equation. Now, the other equation is equating the displacements at the insulator semiconductor interface. So, what this equation says is the epsilon ox electric field in the oxide, this product at this interface must be continuous, which means it must match epsilon s into the electric field in the semiconductor, and you can calculate the electric field in the semiconductor by solving Poisson's equation, and that calculation will have an xd or a phi s dependence on it, and by using this relation you can estimate what phi s is. And what is epsilon ox? It is simply going to be your Vg minus phi s by T ox in a very crude sense, if there are no trap charges in the oxide, etc. So, therefore, you have two relations with phi s in it and you solve for phi s, and these are not easy equations to solve. Okay. So, with that we complete the basic understanding of the MOS capacitor. You know how the MOS capacitor works, the operation of the MOS capacitor, and from this point on we will start looking at some electrical properties, particularly what is the capacitance of the MOS capacitor. We will start quantifying the capacitance, and this piece of information, this knowledge is quite useful when we start talking about MOSFETs.